The broadcast is now starting. All attendees are in listen-only mode.
Okay, so I have to start over, Brian?
Yeah, I apologize. Everyone, we had forgotten to start the broadcast. We apologize. We'll begin again.
I apologize about that. It's our first online training, so I will get going again. Brian, just a quick question. Did you receive a chat in our thing, or how?
No, it was in the questions panel, and it took me a little while to figure out how to pull up the questions.
Okay. Again, I apologize, everybody. This is our first time doing an online training here in Missoula, so I will just get started again. Again, my name is Trent Smith. I'm a forecaster with the National Weather Service in Missoula, Montana, doing the weather spotter training. So the National Weather Service has 122 weather offices across the country and actually in the world. Wherever the United States owns territory, we actually have a weather office there, including Puerto Rico, Guam, and the American Samoas. So we're broken up into 6 different regions. We have Alaska region, the Pacific region, Western, Central, Southern, and Eastern. They kind of oversee the weather offices there. And then we actually have what's called river forecast centers. Our closest one is actually located in Portland, Oregon. Again, the river forecast center, their job is predominantly what they say it is. They forecast the rivers, and we relay that information on. Then we actually have some national centers across there, including the Storm Prediction Center, the Aviation Weather Center, the Space Weather Prediction Center, plus a slew of centers located in Washington, D.C., when our main headquarters is also located in Silver Springs, Maryland. So that's how we're predominantly broken up. So what is our area of responsibility? Here in Missoula, we forecast from the Canadian border down to Lemhi County, from Butte and Homestake Pass over to Grangeville and the Camas Prairie of Idaho. This is our area of responsibility. This is where we are the experts for. So we collaborate with all local, state, and federal agencies to help them with their weather decisions within the magenta colored area. We are surrounded by 5 other forecast offices: Great Falls, Spokane, Pendleton, Boise, and Pocatello. We collaborate quite efficiently with these surrounding offices to make sure the forecast we're producing matches up with their forecast. And then also, when one storm is in such as Spokane's area, we coordinate to make sure that the next office, such as Missoula, is keeping an eye on it and what the storm has been doing. So we have many ways of communicating back and forth with our surrounding offices. But again, our main focus is in this magenta color. We are the experts for this region. So we call it the Northern Rockies of Western Montana and North Central Idaho. So what do we do? Well, our primary job is that we provide the forecasts for the areas. So what does that entail? We looked at model data from multiple different models. We have dozens upon dozens of different models that try to predict what the weather is going to be like in the future. We assess that model data, and we try to translate what we're seeing in the models into tangible weather elements such as temperatures, chance of precipitation, cloud cover, and wind. So we produce these forecasts at least twice a day. Usually by 3 a.m. in the morning and by 2 p.m. in the afternoon. We take all that model data and we have a program that is very similar to Paint, and we digitally draw out our forecast for each weather element out there, which I think is about 24 different elements. And all the text information that you generally see comes from that actual digital forecast, such as highs near 60 degrees, lows in the 30s, 30% chance of rain showers, under mostly cloudy skies. All that text is actually coming from a digital forecast that we produce in office. Probably another big part of the forecast that we do, especially here in the Northern Rockies, are called fire weather forecasts that we do for wildland firefighters. So anytime there's a wildfire, they can submit a request for one of these forecasts. We really focus in on that, give them a forecast for just a point where the fire is, a very detailed forecast, and ship it to them. So that's one of our primary jobs here in the Northern Rockies. Another thing that we deal with is hydrology. So anytime that a river is forecasted to go near flood stage or above flood stage, we are the ones that disseminate that information out to emergency managers and to the general public. Again, the river forecast centers produce the forecast of the rivers, but we're the ones that relay that forecast out to our partners out in the field. One of the main things that the Weather Service also does is all the watches and warnings. The National Weather Service are the only ones that actually issue severe thunderstorm, tornado, winter storm warnings, and such as severe watches also. So again, no other agencies are allowed to do this. That's transmitted out to the public. So anytime that your favorite show is interrupted by the National Weather Service issuing a severe thunderstorm warning, that is actually coming from us. A big thing that we've started doing extensively here in the last 10 to 20 years is really helping with the decision support of our partners, local, state, and federal. We're really getting to know them, to know what they need and what their concerns are when it comes to weather, and we try to tailor that information to the best possible way for them to understand it. So we've been doing that extensively. Data collection, ever since the Weather Service has been around or even thought of, we've been collecting data. We store it in Washington, D.C. at the National Climatic Data Center, and that's just where all that information is stored throughout the country. That data is also plugged into our model data, and so that way models can continue to improve. Training, we do a lot of trainings such as this one, plus we also produce trainings for wildland firefighters and any kind of trainings that people request. We generally are willing to provide it, such as local organizations and such forth. Incident summaries, anytime that there's a huge event or some kind of large incident, we will go out and study the environment and the situation and write up a report about it. And then we also assist organizations with their planning and preparedness for any kind of weather. One that just comes to mind is such as any large outdoor events. We sit down with many organizers of outdoor concerts or the fair and figure out some kind of weather plan and how we can assist during that kind of information can be passed along between each office or each partner. So I will be going through the weather elements. So probably our number one type of storm out there is called the single cell thunderstorm. Usually these only last maybe 30 to 60 minutes. They have a pretty short lifespan. I've seen some that only last maybe 15 minutes where they're just kind of up and down. They could produce severe weather or damaging winds, but predominantly they're just a really short-lived, heavy rain, maybe some gusty winds with them. But again, a very short lifespan. They usually go straight up and come right back down in generally the 30 to 60 minute time frame. Stepping up from the single cell is called the multi-cell thunderstorm, where this is where one thunderstorm develops. It puts out what's called the gust front or the little cold front associated with it. That little front can cause another thunderstorm start to build behind it. And then that storm puts out a gust front and starts building another storm. And all these storms could start training over the same area. A big concern with the multi-cell thunderstorms is the potential for rain to steadily hit the same spots over and over and over again, or if the whole line is stationary, just one area is getting extensive amounts of rain, which could cause flooding or even flash flooding concerns. The multi-cells do have the potential to produce severe, such as in the way of hail or gusty winds. But their main concern for us is just the training of storms over the same area, producing large amounts of precipitation. And then the one storm that is kind of the classic severe weather producer is called the supercell thunderstorm. These are very strong, long-lived, persistent storm. They usually are rotating. And they just have kind of this barbershop pole kind of striation through them as they rotate. These can last at least an hour, maybe up to 3. There has been studies of them lasting multiple hours, up to 6 hours at a time. Supercells tend to be on the severe side. They generally do produce at least severe hail, which is at least 1 inch in size or larger, damaging winds, which are wind gusts in excess of 58 miles per hour. And generally, tornadoes are associated with supercells, but as I will describe later on in this presentation, that's not always the case. So what does a supercell need? Well, it kind of needs to be having a directional change in the winds as you go up in height. Like the winds could be subtly right at the surface, but they could start trending towards more of a southwesterly at the mid part of the storm, and then due westerly at the top. That change in direction with the wind as you increase in height really helps rotate that storm around. And the vertical velocities within the storm could reach over 100 miles per hour. So this is kind of just a picture of what a supercell thunderstorm looks like. And again, it kind of rotates counterclockwise as that surface wind gets wrapped up. And again, there's just different aspects. Your heaviest rain and largest hail is usually going to be on the northern part of the storm. And again, it kind of also depends on the storm movement associated with it, but usually in this quadrant that you see it. And then there's a secondary outflow that could occur called the rear flank downdraft. So how these all interact can help determine if there's going to be a tornadic or a tornado to develop. And again, conditions have to be just right for all these elements to come together for a tornado to develop. So just another picture of what a supercell can look like. Again, in the background is that rear or that forward flank downdraft with all that rain and hail. This whole storm is just kind of rotating like a top. That strong upward velocity, vertical velocity can actually punch through the stratosphere, which is an extremely stable layer, giving us an overshooting top. And here's that rear flank downdraft that we were associated with that can actually help with the tornado development. And then kind of right underneath that good updraft portion, we could get what's called a wall cloud, which is kind of a lowering, a small section of the cloud base really starting to lower, and get a rain boot, which is pulling in the cold air from the rain shaft up into it. So it kind of starts looking like a boot. And it's generally from the wall cloud that we start seeing tornadoes potentially develop. So here's just a couple of images of a supercell across the country. And one of my favorite images of a gift, this is what's called a low precipitation and LP supercell. So there's not a whole lot of rain associated with it. So you can really get to see the cloud formations, the striations of the storm as it's rotating. So what does a supercell look like to us while we're sitting at the office? Well, again, we're located in Missoula, Montana, and we forecast from the Canadian border down to Lemhi County. So we rely very heavily on our radar. So our radar sends out a pulse of energy. That pulse of energy, as soon as it hits any kind of precipitation, such as rain or hail, gets bounced back to the radar itself. So it sends out a pulse and then it listens, sends out a pulse and then it listens. And in doing so, we can get these reflectivities of the storms in our forecast area. This example is actually from the Great Falls radar, and this down here is the velocity of the storm. So again, with those pulses and the listening modes, we can actually detect which way the winds are blowing, if it's away or towards the radar, and actually how fast they're moving, and that way it can actually gives us an idea if that storm is rotating. So when we have a red and a green really close together like this, it typically means that that storm is rotating, and this is what the reflectivity looks like. Here in western Montana, north central Idaho, we do get supercells move through the area, but they're not as common as what you get more out on the plains of Montana. So east of the Continental Divide gets significantly more supercell activity than what you get in the mountainous terrain. So another part of a storm system is called that shelf cloud. So as I was making mention earlier, under a thunderstorm, we get this gust front, this cold air that descends to the ground due to the precipitation. That gust front can actually move well ahead of a thunderstorm, sometimes a couple of miles ahead of the storm. And that cold air, as it's moving along the ground, can actually lift up that nice warm air in front of it. So when that cold air is pushing in, it's lifting up this warm air, and it starts turning it into a nice cloud base that we call the shelf cloud. And again, it's indicative of some strong winds about ready to hit your area, and some of these gusts could be damaging. So it's a very kind of this wedge-shaped cloud formation. I'll have another example of it, but on a slightly larger scale. And then like the wall cloud, as I was mentioning, we had this big thunderstorm sitting up, and now we have this cloud deck lowering below it. And it's generally right underneath the outdraft. And you can start seeing this rain boot develop, and the rain boot always kind of points towards that the rain shaft that's occurring with these storms. And it's in the wall cloud that's got the tightest rotation and has the best potential of producing a tornado, because that storm is just rotating pretty dramatically right underneath the wall cloud. So another weather element is called the squall line, and this is kind of indicative of that shelf cloud, but on a lot larger scale. It's just this huge thunderstorm, line of thunderstorms that are developed right behind a cold front, or a thunderstorm produced a gust front, and tons of storms develop along it, and they can just start chugging along. These storms could be quite massive, several miles long at times. If they get too big, they turn into what's called a derecho, and a derecho is just a line of thunderstorms producing strong winds that are about the size of a state. They can be in excess of 100 miles long, this line of storms. Derecho just went through the state of Colorado and up into Nebraska just a week or two ago, which is pretty impressive, especially to go over to the mountains. So when it's really large, it's called a derecho. If it's middle size, we call them a squall line, and if they're pretty small, we call those a bow echo. So we have had several bow echoes develop here in western Montana, and again, the main threat to these is the gusty winds, strong to damaging winds associated with it. But it's not uncommon to get a little bit of a spin up between the cells and get a tornado to be produced, especially out on the flatter terrain east of the Continental Divide. And here's just a picture of one of those squall lines. And again, it's just got the classic shelf cloud look, where that cold air is pushing up that warm air, and it's just making this nice flat line of a cloud that looks like a shelf. And again, very indicative of really strong winds moving into the area. Squall lines can move in excess of 60 miles per hour with winds measuring up to 100 miles per hour behind it. And again, that's kind of on the high end, but it is possible to encounter such a phenomenal situation. So how is actually lightning? So if we have a thunderstorm, that means that there has to be lightning to create the thunder. And exactly how is that lightning produced? Well, the collision of the water and ice molecules within the storm itself actually transition between a positive and negative electrical field, with rain, water predominantly being negative and the ice predominantly being positive. And again, this is just a very simplification of what's actually going on in the thunderstorms. I just learned yesterday that that is a lot more complex than what's really happening in a thunderstorm. But in general, that there is an imbalance of the positive and negative electrification of molecules. And Mother Nature doesn't like to be in imbalance. So it's going to start trying to find a way to discharge that energy to try to become in balance. So what's going to happen is the thunderstorm is going to send out little, what's called step leaders. So they're just like little tiny sparks, and they're just trying to find a path of least resistance to make a contact. And it's very similar to the static shock. If you rub your feet on carpet and you touch a metal and there's electrocution, a little electric spark. It's the exact same concept, just on a much grander scale. So the thunderstorm will send out step leaders to try to find the path of least resistance until it can make a contact between a negative and a positive. And once it makes that contact, that's when we actually see the lightning bolt. These lightning bolts can occur in the cloud to cloud, cloud to air, but the most impressive ones are actually in the cloud to ground scenario. On average, lightning kills about 28 people each year here in the United States, which is a huge improvement. Just even 15 years ago, we were averaging about 50 fatalities a year. So the National Weather Service has really been hitting hard since the early 2000s with their slogan of "When thunder roars, go indoors." It's really tried to educate the general public on lightning safety. But lightning is very impressive. So each lightning bolt warms the air, or is as hot as 50,000 degrees Fahrenheit, which is actually hotter than the surface of the sun. The latest studies say that lightning bolts can have volts over 500 million volts of electricity with upwards to 50,000 amps. So one of these lightning bolts, if captured and able to be stored, could easily light a small town for many days or even months at a time. And all of that energy is coming into the size of about a quarter of 1 inch. So the video that I'm about ready to play for you all, hopefully this works through the online process, is of one lightning bolt. And it's used by a high-speed camera that's taking 10,000 pictures per second. So what you're going to see here is all the little step leaders leading up to an actual lightning bolt. And you'll know when the lightning bolt actually hits because the whole screen goes white. But all the activity of these little step leaders sparking out happens so quickly that the human eye is unable to process it. So I'll let it run through at least once, maybe even twice, so you can see all the different little sparks and step leaders that occur right before a lightning bolt hits the ground. So again, you see all these little tiny sparks And those are what called step leaders. And again, they happen so quickly that the human eye cannot detect them. And there's so much activity that actually occurs before the lightning bolt makes contact. Again, we haven't actually seen the lightning bolt yet. Boom, right there. So this is another reason why lightning bolts have branches on them, is the different little step leaders coming off of that one main bolt that can kind of give it that branch-like nature. So again, there's just so much activity that occurs prior to a lightning strike. So, and again, so much power associated with one of these. And there's the lightning bolt. So another aspect is hail with thunderstorms. Again, just actually yesterday, a good portion of Northwest Montana encountered either large quantities of small hail, or actually did experience some hail up to the size of quarters. So what exactly is going on with this? So we need a good thunderstorm that has a fairly strong updraft, which is just pulling in all this moisture up and over. So this more moist air turns into rain. That rain gets pulled up by the updraft, and then at some point it actually cools and turns into ice. The interesting thing about water and rain is that it can actually stay in liquid form below 32 degrees Fahrenheit or below freezing. Surprisingly, water could actually stay in this liquid form up to minus 40 degrees Fahrenheit. So it can be called what's called super cooled. So at some point that water gets pulled up and it gets turned to ice. And again, that water needs something to freeze onto, like a dust particle or a piece of smoke, or some kind of, it needs something to grasp onto before it can turn to ice. Then that gets lifted up and turns into ice, then it falls back down, picks up a little bit more water, then gets pulled back up into the updraft, so it freezes again, and can continue to do this upward and downward cycle. So again, it'll just sit here, pick up water, turn it to ice, come back down. Water, ice, come back down. Water, ice, and it can do this trip multiple times. If you take a hailstone and you cut it in half, you'll actually see the rings of each of the paths. So right here, it's a hailstone that's been cut in half, and you can almost see each trip that it made up and down within the thunderstorm. So these hailstones can actually become fairly large and fall to the ground in excess of 100 miles per hour. Even golf ball size hail can do significant damage. I believe in this case, this was a tennis size hail that fell. I believe that this image is from Butte with some wind associated with it. It did some significant damage. But the hail can actually do some significant damage to the human body itself. I believe this was just golf ball size hail that hit this gentleman while he was out and about. So again, if there's a hailstorm or any kind of storms, please seek shelter. And the largest hailstone actually fell in Vivian, South Dakota, I believe in 2014. And the hailstone was actually about the size of a volleyball. Crazy thing is I was working in Goodland, Kansas when the previous record holder occurred, and a mention came out of Hastings, Nebraska, which was the forecast office. So they issued the LSR saying volleyball size hail, and the hail was actually causing holes in man's roof large enough for him to climb through. So these hailstones are just gigantic and can do significant damage. So getting hail this size is a rarity, but it's happened at least 3 times that I'm aware of. Again, once in Coffeyville, Kansas back in the 70s, and then again in Aurora, Nebraska back in 2004. And this image, the current U.S. record holder is from Vivian, South Dakota, and I believe that was in 2014. So another issue that we have to deal with thunderstorms is called microbursts or straight line winds. And again, many areas have been encountering straight line winds here in the western Montana and north central Idaho for the past several weeks to months. So what is it? Well, again, that rain that's associated with thunderstorms can actually pull down some stronger winds aloft. But also just the rain itself coming down hits the ground and starts spreading out and causing a gust front associated with it. So when you get that gust front where you see that shelf cloud, that's associated with more of the straight line winds. Winds can be in excess of 100 miles per hour during these events. But the image that I have here is actually what's called a microburst. So a microburst is a very intriguing event. It's one of those storms that you see that it's raining, but the rain doesn't appear to actually be reaching the ground. Well, that's actually called Virgo, when the rain isn't actually hitting the ground. So what's happening there is that as the rain is falling, the surface is so warm and dry that it's actually causing the rain to evaporate. And that evaporation actually causes cooling. It's the same process of what the human body goes through. So when you're sweating, and it's to help you cool by evaporation. So that rain is evaporating, it's cooling the air. Well, that air becomes heavier, more dense, and it's going to be pulled down to the ground by gravity. And gravity is actually an acceleration. So the farther that cold air has to fall, the faster it's going to speed up, and that falling property will hit the ground and spread in a circular pattern across the area. So as that cold air just hits the ground, it spreads out and actually can cause some significant damage in a very circular pattern. So a straight line wind event is when winds are going kind of in one direction. A microburst will actually look like a nice circular formation, especially if trees are falling. The trees will fall in a circular motion. And if it's a tornado, well, they'll be scattered in all sorts of different directions. So that's how we can depict between the three different kind of wind events that you can have with a storm. Microbursts can cause significant issues with aviation. As you can see, this picture was actually taken in an aircraft. If that plane would have flown right underneath that microburst, it could have easily been pushed right into the ground, causing an accident, which has been known to occur with the aviation community. So here's just what some straight line wind damage kind of looks like as it moved through. This is the Mission Valley back in, I believe, 2004. And this event happened in the early 2000s up in Libby. This was a drive-in movie theater. The fence was taken out. Thankfully, nobody was harmed in this. But I know for many years, the sign outside the movie theater says, now playing Gone with the Wind. So it was just kind of a play on the storm, on the movie theater being closed due to the windstorm. So one thing that we actually deal with here in western Montana is actually called the non-supercell tornado. So these are tornadoes that aren't actually associated with a thunderstorm themselves, particularly a supercell. So what actually is happening here is that we can actually have a boundary right along the surface where the winds are actually blowing at each other from opposite directions. This is quite common up in the Flathead Valley, where they can actually have an easterly wind, so a wind that's blowing out of Bad Rock Canyon near Columbia Falls, so they'll get this little bit of an easterly push. And then on the other side of the valley, they're getting a nice westerly wind just from the synoptic winds aloft. So when those two winds collide, they just kind of make this boundary with a little bit of turbulence, a little eddies. And then every once in a while, if there's just enough upward motion, a few showers that come through, those showers can actually pull those eddies upward, and that spinning can be pulled and stretched and actually cause a tornado to form. And this pulling and stretching is the kind of the same concept as figure skaters, is when they start spinning, when their hands are far out above them, that are out away from their body, they move really slowly. But as soon as they start pulling in their arms close to their body, they'll start spinning even faster. The same concept can be experienced if you're ever in an old tire swing that's with a rope and it gets all wound up and you hop in the center. If your body is stretched out nice and far, the tire swing will just start spinning really slowly. But as soon as you start pulling in your arms and your legs closer to your center of gravity, that tire swing will spin quite rapidly. So another way that a tornado can form, but predominantly a dust devil, is that just stronger winds aloft, just slightly above the surface, can actually cause a horizontal eddy to form. And if that horizontal disturbance moves over a warm pasture or some black dirt, it can be lifted upward, and that can actually cause what's called the dust devils around the area. So that's predominantly how they're formed. But if one of these storms actually gets attached to a cloud base, then it actually turns into a tornado itself. So in 2009, up in the Flathead Valley near Kalispell, that notion of easterly winds coming out of the Bad Rock and westerly winds on the other side of the valley creating an eddy actually did create multiple tornadoes across it. At one point, they actually had 3 tornadoes on the ground. As in this picture, you can see the one in the foreground, and then there's a fainter one in the background. Again, these lasted for several minutes. Thankfully, non-supercell tornadoes are generally not that strong, but they can get up to EF2 level, which can take roofs off the building. But again, that predominantly they are fairly weak and just kind of blowing dust around, but they do have the potential of becoming quite strong. So we do get non-supercell tornadoes are one of the more common tornado events that we have. But again, on average here in western Montana and north central Idaho, we average only about 1 tornado every 3 years. So it's a pretty big rarity for us. If you get east of the Continental Divide, tornadoes are more frequent out there. So the supercell tornado, again, has a lot more associated with it, just the strong rotating updraft, how that rear flank downdraft is associated with it, the stretching of that spinning air as it makes its way to the ground. So there's just a lot more mechanisms associated with a supercell tornado. Some that we understand, some that we actually fully don't understand to even this day exactly how does a supercell tornado form. There's still some microphysics that we're in the process of researching. But some of the records that we've encountered from these tornadoes, supercell tornadoes, is one has been as wide as 2.6 miles. So that's pretty impressive. That's how wide the tornado itself was. One tornado, the May 3rd of 1999, tornado down in Moore, Oklahoma. They actually had a mobile radar close by. They measured wind speeds in excess of 300 miles per hour with that tornado. And the longest lived tornado was on March of 1925. One tornado stayed on the ground for 235 miles. So these supercell tornadoes can be quite dangerous and long-lived. The majority of the supercell tornadoes are associated with more of the plains, kind of in that tornado alley of Texas, Oklahoma, Kansas, Nebraska, Missouri, Iowa, just where the nice warm moist air from the Gulf of Mexico can intermix with a cold front that's fairly dry that's coming out of the higher plains of Colorado and Kansas. So we just need the right ingredients to get these kind of formations. And just got some images of different tornadoes Sometimes a large tornado can actually move into multi-vortices. So you can actually have multiple tornadoes on the ground that are kind of making up one large tornado. Again, trying to understand the microphysics of a tornado. We're still researching all that. But multi-vortices is actually quite common within these larger tornadoes that encounter. And here's a very large tornado, but even under these large tornadoes, you could predominantly get a second tornado called a satellite tornado that comes off of them and moves and rotates around the main storm itself. And again, an EF5, that's the Enhanced Fujita Scale. Ted Fujita was a scientist back in the 70s that went out and actually studied tornado damage. An EF0 is a tornado on the ground that caused 0 damage, where an EF5 was a tornado on the ground and all you had left was the slab of the home. So in this instance, we have multiple homes that there's just nothing left, and so we categorize those as an EF5. So when do we generally see our predominant severe weather? Well, any kind of severe for Western Montana. Again, here in the Northern Rockies, we don't actually see that much in the way of severe weather. But generally, the first week of July is our best chance at seeing any storms. And again, this is a 1% chance on any given day in that first week of July that we could see some thunderstorm activity. And again, we predominantly see our thunderstorms across Salmon, up Idaho, up into Butte. So just kind of in this general area. So for hail, the best chance climatologically to see hail is the second week of July. And again, the scale is a little bit different. This is 0.25%. So on any given day in that second week is our best chance. But again, severe hail can actually happen anytime in the summer. But climatologically, the second week of July is the best chance for the Northern Rockies. But again, we just saw severe hail across northwest Montana just even last night. And then wind is generally our best chance. Again, the scale is a little bit different, 0.25% on any given day in that first week of July is our best chance. But we can get severe winds well into September, October timeframe associated with thunderstorms. So another aspect that I discussed earlier is the river flooding. The main concern for river flooding is November through June, with the peak hitting between May and June. So why May and June? That's when we're melting the snow and our rivers are running high. And then if we get a heavy rain event, which could actually cause those rivers to swell even more and actually cause some significant flooding across the region. So again, we can have some where we've actually experienced some pretty significant river floodings back in November. I remember a case up in Glacier National Park where in November we just got a really heavy rain event in November, caused a lot of flooding damage. But again, our peak is usually that April, May, and June timeframe with the snow melt. So as one of our slogans, turn around, don't drown. If you, in this picture, the bridge for the river is actually in the background, but for some apparent reason, the river decided to make a new channel in the foreground and totally take out the road. You don't know exactly how deep is that water, and it could take as little as 3 inches of moving water to actually start moving a car sideways or start pushing it downstream. An SUV or a large pickup, it takes as little as 6 inches of moving water to actually start floating an SUV or a large pickup downstream. So again, if you can't see the bottom and you don't know exactly, turn around, don't drown is our motto. Another concern about the May-June river flooding is all the debris in the rivers from the winter months and on the hillsides can start clogging up. All these logs can get jammed up against a bridge and actually cause a nice log jam and back the water up, which can actually enhance the flooding, especially behind that log jam. So that is another concern that we have to deal with. This wood debris was actually on the Clark Fork near Missoula several years ago. And sadly, this video didn't get uploaded, but it's just the raw power of the water flowing near the Swan River near Big Fork. So unfortunately, I can't play that. Another area that we have to deal with is flash flooding. Again, that's just excessive amounts of rain that falls in a short period of time. For the majority of the forecast, for the majority of western Montana and north central Idaho, we only need 2 inches of rain per hour to actually get some flash flooding. In this case that I'm highlighting here, there's a storm that just developed north of I-90 near Drummond, Montana, and it produced about 1 to 2 inches of rain. All that rain came down these gullies just north of the interstate and actually caused a river to flow across the river, the interstate, and actually had to be closed for a while. So, and one vehicle was actually swept off of I-90. So, again, these are very short-lived, but can actually produce a lot of damage in a very short amount of time. This was actually a picture from a gentleman just south of Drummond. And all this piled up here is actually hail that was associated with that storm. It was just a slow-moving thunderstorm. I went over the area, dumped tons of hail and tons of rain. And at one point, the farmer said that the water was running as high as his fence post, about 3 to 4 feet above ground. So, and that water really dug trenches as deep as 4 to 6 feet in the hillsides around it. So, some extensive raw power, so we can definitely get some flash flooding, especially with slow-moving thunderstorms. And again, burn areas, especially recently burned wildfire areas, it could take as little as 1/4 of an inch of rain in 1 hour to actually start causing some flash floods. This flash flood event will happen near Drummond, Montana, after their big wildfire season in 2001. And as you can see, that flash flood actually removed all the topsoil and it was eroded all the way down to the bedrock in this one gully. So just the amount of debris associated with it can just come out and fan out and do a lot of damage, especially to properties. This shed and house was luckily spared, but again, we are concerned about houses that are just at the foot or at the mouth of a gully after a recently burned area. So we do actually send people out into the field to assess burn areas and how much rain would it take to actually cause flooding. And we keep that data in-house so that way we can make decisions on flash flood products for the next couple of years. Landslides is another concern. So landslides generally happen in the springtime when the snow is melting and saturating the soil, and then we can get a rain event, which actually just takes it, just that soil just beyond its limit, and actually starts it to flow downhill. This landslide was down in Lemhi County back in 2009. This was a roadway near Orofino, Idaho, one spring where the road collapsed and eroded. And this was actually a hairpin turn. All the debris flowed down onto the roadway right below it. So this took quite a while for them to fix and stabilize again. But again, it's just due to that saturated soil, due to the snow melt, followed by a rain event. And just a little humor, just a bit of speed up, just a little bit of speed, you got this. Probably the most impressive landslide that I've ever encountered was a early spring event. Again, the snow was just starting to melt, but we got a pretty good 1 to 2 inch rain event over Idaho, which just caused this massive landslide down onto Highway 13 going up to Elk City. This boulder this large boulder right here was about the size of a small house. It took them 2 attempts to break it up to small enough pieces for them to haul it away so it wouldn't impose any more danger on the roadway. So this took weeks for them to clear off. So landslides are a concern that we keep an eye out for. So another thing that we deal with quite a bit is snow. Temperature plays a big role in what kind of snow and what kind of snowflakes you're going to encounter. Again, that snow type, because you can get little flat flakes, which can just give you kind of a dusting or fairly flat snow, heavy dense snow, to dendrites, which can give you big fluffy snow and large amounts of it. So the temperatures really determine what kind of snow types we can have. And again, we're looking for that perfect -10 to -18 degrees Celsius in the atmosphere to give us those dendrites. And again, the dendrites are usually the type of snow that causes large amounts to fall. Another concern that we have is freezing rain. As I spoke earlier, water is kind of a tricky. Water can stay in liquid form well below freezing. So generally what happens in a freezing rain event, especially here in western Montana, is that we get some cold air trapped in the valleys of western Montana, north central Idaho, especially after an Arctic has moved in. Cold air is heavy, it's dense, it likes to settle into the valleys itself, and we can be below freezing. And then right above that freezing air, it can be relatively warm during those big Arctics. I mean, it can be well below freezing here in Missoula, but you go to the top of Sentinel mountain, and it can actually be quite mild, up into the 40s, maybe even 50 degrees. So when a storm system comes in, it could be snow way up high, but it hits that warm layer near Sentinel, turns into rain, and then that rain falls back into that below freezing air. And as soon as it touches something, it freezes instantly. Again, water needs something to freeze onto, a dust particle, your car windshield, tree limbs, the road surface. So freezing rain is a pretty significant event, especially here in western Montana. And each valley can be very different. One valley here in western Montana could be experiencing snow, the next valley could be having rain, and then another valley can be having a freezing rain event. So it's quite hard to forecast sometimes, just due to the variation and the complex terrain that we're in. So the importance of spotters. So here's an event from 2015. It was a major rain event that we were forecasting. This was in February 3rd of 2015. We're looking at this really warm system moving in, causing widespread rain, not snow, but rain. And we're looking at anywhere from 1 to 2 inches in the higher terrain. And again, predominantly north central Idaho. Here's Orofino with 1.23. Missoula, we're only looking at 3,600s. Kalispell, 8/10. And then up in the mountains of Glacier Park, we're looking at upwards to 3 inches. So we are highlighting this. We are telling people about this big rain event. So what are some of the impacts that occurred with this? Well, Interstate 90 was experiencing some rockfall and landslides. So they had to close down a couple of lanes at times. On Highway 12 near Lolo Pass, a large chunk of boulder broke off and fell onto the highway, closing it for an extended period of time. But the more surprising thing is, down in Salmon, Idaho, I was actually working this event. We were all concerned about all this rain, and we forecasted that well. But Salmon, Idaho, we got a phone call from the emergency manager asking when all this widespread flooding was going to stop. And we're like, flooding? What flooding? You haven't even reported any rain yet, and we're only forecasting 2/10 of an inch. So what happened here in Salmon, Idaho is that they had 6 inches of snow on the ground. And the night prior to the rain, it stayed really warm. Temperatures were in the 40s all night long. And all 6 inches of that snow melted in one night and caused multiple little creeks around Salmon to flood, causing extensive damage to basements and to other properties. So again, our focus was on the big rain event, but the biggest impact was actually from Salmon, Idaho, who hadn't even received a drop of rain yet when this occurred. So let me highlight, again, our radar does wonderful things, but our radar actually sits at 8,000 feet above ground on top of 0.6. And the lowest slice of our radar that we can see is a half a degree. So you take that half a degree at 8,000 feet and you take it out to like northwest Montana or down to Riggins, Idaho, or southern Lemhi County, Homestead Pass. There's actually a lot of the atmosphere that we're not actually able to see with our radar. And this is particularly difficult in the wintertime because our systems in the winter don't actually get very high, and our radar can actually overshoot it. So if you saw this radar picture, you'd say that the areas between Orofino up to Polson is getting the most snow, and that everywhere that you see black isn't encountering anything. Well, that could actually be very misleading, because over here at Whitebird Grade, just south of Grangeville, our radar is not indicating anything, but as you can see in the camera picture, they are actually experiencing some pretty good snow on that roadway. So what would we like our spotters to report? Well, any kind of tornado, funnel cloud, or water spout, any kind of major rotation of the clouds that are spinning pretty dramatically, please give us a call. High winds estimated at least greater than 40 miles per hour, because at 40 miles per hour, we can actually start encountering some damage around the area. Heavy rain of a half an inch or more per hour, because again, it doesn't take a whole lot for those burn scars to start flooding. And again, flooding of any kind, you see major ponding of water on the roadways or in fields. Hail, a quarter of an inch or larger. Visibility being reduced to less than a quarter of a mile. We get actually a lot of phone calls from people who live on mid slopes or about mid mountain up, and they can be in pretty heavy fog while the rest of the valley can be pretty clear. So it'd be it'd be good to know that kind of information, especially if there's roadways moving through it. Heavy snow, we're looking at about 1 inch or more per hour rates. Weather related, any damage or injuries. And this one is one that we're really starting to hit home is if the weather is causing you personally a moderate to high impact, we would like to know about it. It might not fit all these categories, but just the rain itself is causing you issues. We would like to know, so that way we can get that kind of information out also. So we kind of leave that up to interpretation. Everybody is going to have a different limit on what a moderate to high impact is. So probably the number one way of letting us know is by calling our 800 number, which is 1-800-676-6975. This telephone number will ring into an answer machine. As soon as you call it, it's going to give you two options. You can either leave a message, or you can press, I think it's 2 to actually talk to a forecaster. If you press 2 to talk to a forecaster, it'll ring through and a person will actually answer it and answer all your questions or take your information. But if you do decide to leave a message, it's very important. Please leave your name, your approximate location, the date and time of your observation, and what you are reporting. If we don't have all this information, we won't know exactly who or what or who or where you're at, which can be a big deal. We've received many phone calls just saying, just wanted to let you know we're receiving a quarter-inch hail. And that's all the information that we're given. So we can't really do much with that information, especially with everybody having cell phones. Please give us your approximate location, just not your name, because if you give us your name, we're going to assume that you're home and that's where you're observing it. Or if you're out and about, that approximate location will help us really dial down into it. Another way of relaying information to us is by Twitter. You can just do a direct message to us or kind of sign it at NWS.Missoula. Facebook, we're on Facebook. We do have a YouTube channel. If you go to YouTube, go to NWS Missoula, Montana. We do produce 3 briefings a week, and we upload those to YouTube. A lot of our information can be found on our main website, which is weather.gov/Missoula. And please remember the .gov. If you're going to .com and you're going to start complaining about the forecast, I can't help you. We're weather.gov. So, and you can find a slew of weather information, so much that it can actually boggle your mind at times. And then we don't actually have an app, but you can go to mobile.weather.gov on your cell phone to get the basic forecast and some other information. Some other ways of reporting is by there is a submit a storm report on our main page where you can submit it and it'll ring a bell. Or there is an app called MP that you can download that you can submit information and it'll show up within our office. So just a multitude of ways of getting your information to us. So, and I don't actually have it here, but you can also email us. I will, as soon as the end of the presentation, I'll try to bring that up to you. And then you can email us at mso.media@noaa.gov. So let me just escape here, and I'll actually put that up. Let me do a new slide right here. So it's just mso.media@noaa.gov. So you can email us this, email at us at this email address, all your pictures. You can send text messages to this link. So a lot of information can be gathered that way. So for the most part, I'm done with the basic National Weather Service spotter training. If you want to take your weather spotter training to the next level, there is an organization out there that is supported and endorsed by the Weather Service. It's called COCORAS, which stands for the Community Collaborative Rain, Hail, and Snow Network. And what COCORAS is it's just a community-based volunteers who are collecting daily precipitation and inputting it into a web base. So in general, with the National Weather Service, our data collection is roughly every 26 square miles. So that's a fairly large area. But COCORAS got started after a major rain event in 1997 that hit Colorado, where they went out, the Colorado state climatologist went out and did a survey and realized that the Weather Service wasn't getting enough accurate information that they did not take into account a thunderstorm that produced 17 inches of rain over the top of the hillside that caused extensive flooding across Fort Collins, Colorado. So he started this organization called COCORAS to help try to improve the data collection. And their goal at COCORAS is to get out of the rural areas for an observer every 6 square miles, and in urban areas, 1 every square miles. So again, what they're doing is they're taking this 4-inch rain gauge that can be purchased off their website for as low as $25 when it's on sale. Generally, it's running about $35. You go outside once a day, every day, you take your measurements, and then you plot it into their website. They actually have an app on the phone that you can actually input your data. And again, it's just a whole bunch of volunteers. So just an example, here's what the precipitation map looked like without COCORAS data. This is just the information that the National Weather Service got from their general observation posts. But then once you actually start inputting the COCORAS data, you can actually see where that data has helped enhance the precipitation map. So the data is invaluable. We get this data in our office. It's collected within the National Weather Service. But if you want to take your spotter just to the next level, I encourage you to look into CoCoRaHS. Again, the information can be plotted on maps. Again, here's just another example of how one observer just happened to be right underneath one of these stationary cells, thunderstorms, and they got 7 inches of rain while everybody else around them only got maybe 1/10 of an inch. So CoCoRaHS really helps out the Weather Service. So I can't say enough about it. So again, just go to cocorahs.org is their website. Obtain the 4-inch training. They have a wonderful training slideshow, but also a lot of videos to help you. And then they teach you how to set up the gauge and just start taking observations. So if you're interested in taking your spotter to the next level, again, I can't encourage this enough. So I am at the end of my presentation. I will hopefully let my coworker open it up and see if there's any questions that I could answer.
So I think all of our questions have been answered. For anyone that did ask a question and it wasn't answered completely, if you just want to unmute yourself, you can just ask the question outright.
Brent, I'm not 100% sure in webinar GoToMeeting that they're actually able to unmute themselves. So if you do have a question that was not answered in chat, or you come up with another question, you have that email address of nws.missoula@noaa.gov that you RSVP. Send your questions there, and we can answer them. Let me go back at the very start of my presentation.
Trent, if you don't mind, I do have a question. This is from someone who lives in Salmon, and they say, people here say this area isn't very windy, but what's happening this year?
So actually, Salmon, Idaho, actually just south of Salmon, Idaho, is actually a very windy spot. Some of our stronger wind gusts actually come in the higher terrain. Ezra Creek is one. Down near Gilmore Summit and Leadore, that's actually one of our windiest locations. So Salmon can be kind of a tricky because it sits right in that bowl of kind of the 3 valleys of right there, and it can be kind of secluded at times. But even if you look at the automated observation sites just south of Salmon, they can actually have quite breezy conditions. So I'd actually say Lemhi County is one of our windiest spots. So I don't think Salmon itself can be difficult at times because, again, how it sits, but it's not unheard of for them to get quite a bit of wind also. So another is, here's my email address, trent.smith@noaa.gov. So if you have any questions, feel free to shoot me an email, and I'll try to get back to you as soon as I can. Do you have any other questions for me, Brian?
Right now, we haven't received any more questions. All of you have received the email to get into this webinar, except for one person. I do apologize to that person. That came from my personal my personal email. Like Trent, you can email me if you have a question.
All right. To follow up on this, probably tomorrow we'll be sending out a form for you to fill out. And this is just kind of our standard spotter form, just to collect your name, your address, your locale, and some basic information on how to contact you. And we'll get you into our spotter database. This is a secure database that we only utilize during severe weather events, or impactful weather events. I shouldn't even call it severe. If we think that there's impactful weather in your area, we might give you a call to see what's going on. But again, feel free to give us a call at that 800 number anytime that you're experiencing any kind of significant weather. So that 800 number is always available. And with that, I think the presentation is concluded. Thank you all for attending. Brian, if you want to end the presentation.
I will in 1 second. I'm just answering one last question here.
Okay.
Actually, it'd be faster to talk about it. This question was someone from Thompson Falls asking about how it can snow all day with zero accumulation.
Well, it's snow, again, it takes a considerable amount of warm air, or a fairly deep warm layer to actually melt the snow. So if the ground is warm, so again, a very complicated situation. I shouldn't say complicated. So the earth absorbs a lot of energy very slowly. And that energy is also released very slowly. So it's not uncommon for the earth itself, the ground itself, to be above freezing, especially if we've had multiple days of, say, 50 degrees, and we've had 4 days of 50 degrees. Well, that earth is going to slowly, the land's going to slowly warm up and be in the 40s, mid 40s. Well, then we could actually have a fairly strong cold front come through, drop the air temperature down to below freezing, let's say 30 degrees air temperature, but that ground is still going to remain 40 degrees. So under that scenario, we can have snow all day, but that ground is so warm. And as long as the snow is not of significant intensity, it'll just melt every time it touches the ground. But there is, at some point, if it starts snowing hard enough, that snowfall can actually overcome the melting and you can get snow accumulations. But generally, that ground, the ground itself is above freezing. And then it's just the air temperature is below freezing. But again, it's actually not uncommon to actually have snow when the air temperature is as warm as 40 degrees because it needs time to melt. There's a lot of different little caveats to that, but that's the general scenario.
They added to their question a little bit later on saying that it was below freezing. So I'm thinking they're talking about the northwest flow type of scenario where there's not a tremendous amount of a tremendous amount of moisture, but it can just snow for a day or two.
Yeah, and again, it just, under right circumstances here in Metro Montana, we can just get steady light snow across the region. And it's just doesn't have a lot of structure to it, and it'll just slowly melt. And again, it's that ground temperature can just be slightly above freezing, even though the air temperature is below freezing. So.
Does the National Weather Service have recommendations for equipment to measure wind speed, temperature, etc., brands that are accurate and reliable?
Unfortunately, the National Weather Service cannot endorse a certain type or brand of equipment out there. Sadly, we're not able to do that. But I know that there's been plenty of research and documentations out there, especially by, I believe the Forest Service has done some research on handheld wind sensors. And I know that there are some reputable names out there, so I just recommend that you do some personal research, but sadly, I can't endorse a certain product.
All right, yeah. Are there any more questions? Well, okay, I would like to thank you on behalf of National Weather Service here in Missoula for attending. Like Trent said, we'll send out an email with the questionnaire tomorrow. And thank you very much for coming.
I hope everybody has a great evening.
All right, give me a second, Trent, and I'm going to figure out how to end the.
Hey, Brian, why don't we go to our Google account and do a video chat there?
Okay.